Hey everybody, welcome to the last podcast ever. I hope it's a shortish one, but I think it's going to be like a 45-minute one. Oop, made you look. Okay, so let's hop right into it. This is the last part. So this is electrochemistry. This is almost all new except for this part. Okay, so oxidation numbers. So the oxidation numbers are really the charge. So elements in their standard state have an oxidation number of 0. This would include oxygen, P4, any diatomic, right? Other ones will just be all by themselves, like iron plus O2. Both of these would have oxidation numbers of 0. O is always -2, except if it's a peroxide. H is always +1, except where it's hydride, specifically these two. Okay? And these are very rare. So welcome to chemistry and exceptions. Trust the outside of the periodic table more than the inside. So what does that mean again? Okay, so this column is +1, that's on the outside. And if it said n is -3, see how this is in the middle? Love the +1, expect -3 to really be something else. Okay, orbital diagrams of full and half full will support the oxidation numbers. So, for example, if I have nitrogen, I'll pop it up here. So orbital diagrams, my goodness gracious, 1s, 2s, 2p, nitrogen has 3. So if I'm looking at nitrogen, so if this is nitrogen, and it is, what you can do is you can lose those 3, and it's reasonable to have n -3 because you have an empty p. Okay? It's reasonable to have this filled and have n +3 and have a full p, right? So that's why each of these are kind of okay. I'm going to go back to what we had before. If I had n plus, so I've got +3. If I have n +5, that would lose 5. That would have a full S. Okay, so you should be able to explain all those charges. Okay, so and then I give the example of MnO4. So oxygen, first rule of oxygen's -2. So that means these 4 are going to be -8. So Mn -8 equals, so Mn equals +7. Okay. Oxidation and reduction, we've done this before too. Oil rig, oxidation is loss of electrons, which is what I say, and gain of electrons is reduction. Okay. Reduction is a gain of electrons. The charge goes down, right? And then you'll be given parts of this. Okay, parts of this. It used to be you were given this whole thing, but now there's just parts of it. This is the reduction potential. Notice how every one of these guys is gaining an electron. Reduction is gain of electrons, right? So these are the best at being reduced because they have the biggest E0, and we'll get to that in a second. Oxidation is loss of electrons, so your charge is going to go up. Lithium yields lithium +1 and +1 electron. It's typically not shown this way, but if it is, E equals 3.04 volts. So let's look at lithium. See how we have this right here? Reduced, it's negative. Oxidized, it's positive. So you flip sign when you flip the reaction. All right. Electrochemical cells. If you get a chance to choose, so we have these new words we're going to talk about. We're going to talk about anodes and cathodes. Okay? The anode does oxidation. Okay? The cathode does reduction. So that means we can remember anox, anode does oxidation, and a red cat. Reduction happens at the cathode. Okay? So, looking at this picture, these are what batteries really are. Got myself a beaker, got myself another beaker. This is a salt bridge. Okay, so ions can flow back both ways there. Instead of a salt bridge, very rarely, but very possibly, you have a super weird beaker with a porous disc. Okay, the wire on top, there has to be a wire between these metals, right? Moves electrons. The salt bridge has ions flow in both directions. Okay, so we know, let's say we have electrons flowing this way. If as soon as one electron gets here, it would be negatively charged, right? And if it's negatively charged, no more electrons would come in. So what has to happen is the negative ion, very often it's KNO3 or NaNO3. So the negative ion will complete the circuit and go into that solution. So it's going to make a full circle, okay? What you have to remember, it's a little hard to remember, we'll get to it in a minute, that the positive ion has to flow the other way, right? So if this is adding nitrate ions, if I'm adding nitrate ions, this would be becoming negative. So we want to get rid of the positive part of that too, and we'll learn how this is created. Both beakers have positive and negative ions in them. So a metal has its ion, and typically it's nitrate. So let's do copper and nitrate, okay? And we'll do zinc, nitrate, okay? Oh, I should look to make sure I have ones that'll work better. So let me check and make sure. So up here, if I do, let's use silver, because I don't think silver is used in the other. So if I do silver, it's going to be 0.80, and then let's go with zinc is negative 0.76. So we'll just make the other one be silver. Okay, so what's going to happen is Ag positive has to be here. Okay, so my solution is going to be this metal, its ion, and a nitrate. This metal has an ion and its nitrate. Okay, zinc is +2, so I need 2 nitrates in there. Okay, so if we have it going this way, the anode does oxidation. Okay, oxidation is loss of electrons. And I have this flipped. So I'm going to change this really quickly because I know this one's wrong. I'm sorry. So I'll make this zinc. And silver. My eraser's not being my friend today. And silver ion. And then the nitrate would have the double nitrates. I'm sorry, the zinc would have the double nitrates. Okay. So both beakers have positives and negative ions in them. The metal has its ion. Red cat, anox. Reduction occurs at the cathode. So reduction means zinc +2 plus 2 electrons yields solid zinc. Okay? Looks like I actually did this backwards again, but that's okay. So when I look at this, if this is what's happening here, what's going to happen is zinc +2 going to plate on here, and it's going to get fatter. Okay? And it's going to release 2 electrons. Hey, look, the electrons are going this way. Right? So this is the reduction chamber. Sorry, I flipped it around. This is the reduction chamber. So red cat, this is the cathode. Okay, the anode does oxidation. So that means oxidation is lost. So silver is going to give me Ag positive plus an electron. Okay, this is oxidation. This is the anode. Okay. Okay, so that's a lot. This is the introduction. Remember, that's okay. Electrons flow from anode to cathode. So if this is the anode, okay. So oops, I did this dude backwards. Okay, yeah. So if this is the anode does oxidation. That means that my silver is dissolving, right? So I start off with a bar, and I end up with a dissolved bar, okay? Because the solid silver is turning into an ion, going away. All right, better picture. Let's see what we can do. Gases are sometimes in these cells. Remember, this whole thing would be called a cell. Okay. Note if there's no metal on the left above, an inert, unreactive metal, we always say it's platinum, will be used. So notice how this reaction doesn't have the metal ion in it, so we're going to use platinum as our electrode. Okay. So this would be platinum. Okay. And that's because it won't react. Galvanic cells are spontaneous. This is the norm. Most of the things we look for are galvanic. If it doesn't say it's galvanic, this means your voltage is positive. Oxidation and reduction, I'm going to add the word both. Both occur. E0 cell is positive. Okay, so let's take a look at what that means to be galvanic. Draw the galvanic cell based on the following half reactions under standard conditions. So remember, this is reduction, the way it's written. This is reduction, the way it's written. I need to have one reduction and one oxidation. So one of these has to flip. If I was a fool and flipped this one, I would have negative 1.51 plus 0.0036, and it would be a negative answer. No, I'm not that foolish. I pity the fool. So what I'm going to flip is the bottom one. So I'm going to draw a line all the way through this and rewrite it. Fe yields Fe3 plus 3 electrons. Since I flipped it, E0 equals negative 0.036 volts. Okay, so what I have to do now is figure out my total voltage. 1.51 minus 0.036, and I'll be honest with you, you know my hatred of the phone calculator. That's all I have right here. I'm in the basement of a hitting facility. 1.51 minus 0.036 is 1.474 volts. That's the total voltage. Notice it's positive, and that's how I get it. Okay, now just to get the overall reaction. Remember how I got rid of this? Let me get rid of this a little more effectively. Boom. Oh. I got rid of this, okay? Now my overall reaction would be combining these. Do you see how I have 5 electrons here and 3 electrons here? We balanced some of these before. So what we will do is we will, on the top part, multiply it by 3. On the bottom, we'll multiply it times 5. And these do not change. Your voltage does not change. I think of voltage as being like natural attractiveness, okay? So if your natural attractiveness is 4 out of 10 and you have a twin, does that make you more or less attractive? Neither, right? It doesn't do anything. It's always your natural attractiveness. So my overall reaction here is going to be 3MnO4 plus 8H positive plus Fe. Oh, I did that one. I remembered one of them. 3MnO4, right? 24H positives, right? 5 Fe's. Yield still 3 distributing. 3Mn2 plus 12H2O plus 5 Fe plus 3s. Okay, that's my overall reaction. Now, so now I got to draw the galvanic cell for this. Okay, so the galvanic cell, we want to put our anode on the left. Anode does oxidation. This is my oxidation cell. Boom, boom, boom. Boom, boom, boom. Anode is oxidation. I'm going to have an iron dude here. This is going to be Fe plus 3. And then I'd have NO3 3 times. Over here on this side, it gets tougher because there's not a metal, right? I'm sorry, wrong one. There's not a metal up here. There's no regular solid metal. So that means my bar is going to be platinum. And inside here, I have everything listed here. MnO4 negative, H positive, and I need the products in there too. Mn plus 2, and water. I'm not going to put water in it. We know that. We've got a wire that goes this way. It always flows from oxidation to reduction, anode to cathode. I have a wet string, which is what we use for our salt bridges. A wet string, which would have nitrate going this way and K positive going that way. All right. Draw the galvanic cell for nickel zinc. Okay, so I got to flip one of these. I'm going to flip this one to make it more positive. Okay. So underneath, I'm going to write zinc yields zinc plus 2 electrons. Wipe out this guy. I don't want to look at it anymore. I forgot to write down this is positive 0.76 volts. And then looking at this, you have my electrons cancel already, so I don't need to multiply it by anything. So remember, anode does oxidation. This is my anode, and I'm choosing to put it on the left. I don't have to, but I'm choosing to put it on the left. So that means my metal stick is zinc. Over here, my metal stick will be nickel. Put it in solution, throw in some throw in the zinc ion, throw in some nitrates, throw in some nickel. Nickel's also plus 2. Throw in some nitrates. Salt bridge with nitrate going this way. K positive going this way. Got myself a wire. My electrons flowing that way. That's it. Okay. Electrolytic cells need to have a battery attached. The voltage of the battery has to be greater than the negative calculated value. Okay? So electrolytic cells, this is the other type of cell. It's non-spontaneous. It has a negative voltage. And you attach a battery with a larger voltage to overcome that negative voltage. All right. So these also have delta G's. Hey, I was wondering why this was in Big Idea 9. Delta G equals negative NFE. Okay? So delta G is in joules, not kilojoules like it was before. And remember, negative delta G is spontaneous. And remember, this is another good one. Positive E is spontaneous. N is the balanced number of electrons transferred from the equation. This one had 2. So we had 2 electrons on both sides. The one up here had 15, right? 3 and 5 was 15. So that's where that number comes from. F is Faraday's constant. So this F right here is often shown as the fancy F. That's Faraday's constant. And that's 96,500 coulombs per mole. That's just a constant. Coulomb is the unit for charge. E is the voltage at standard conditions. Everything's got to be 1 molar. Temperature's got to be 25 degrees Celsius. Okay, 298 Kelvin. Voltage is in V, and people forget to put the unit volts on there. You see me forgot it right here. It's found by adding the half reactions properly flipped. I showed that. Voltage does not change when you double and triple, and I showed you that. The least common multiple, this was the one I did before, right? My least common multiple was 15. But the E naught is still 1.51, even though I did it times 3. So that's the same thing. And I just talked about it. Calculate delta G for a copper silver galvanic cell. So delta G, I'm looking for my delta G equation again. Delta G equals negative N, fancy Faraday, Fe. So the first thing I have to do is find the E of it. Didn't I just do copper 2 and silver? I think I did. No. Oh, I did. No, I didn't do copper 2 and silver. I'm sorry. So I've got to use this right here. So looking at this, here's silver. Here's copper 2. Which one do I need to flip? Well, it has to be positive when I'm done. So I'm going to flip this guy. Okay, so I have Ag positive plus electrons yields Ag, and that's positive 0.80. And then I have, got to flip that one, copper yields copper plus 2 electrons, and that is negative 0.34. When I combine those, I get 0.46 volts. Okay, so delta G equals negative, times 2, right? So that way I have 2 electrons going through it. So delta G equals negative 2 times Faraday, 96,500, E 0.46. Put that in my calculator, and there's my answer in joules. Okay, and it will be negative. Delta G will be negative because the reaction is spontaneous. All right, E equals E naught RT over NF ln Q. Ooh, doggies. So this is E at a non-spontaneous condition. So you can change the voltage by changing the temperature. Notice how that's not a constant. And the concentration, Q. So remember, Q is, well, it's products over reactants. Oh, come on. It's products over reactants. Remember, it had to be in molarity raised to the coefficients. So it won't be at equilibrium, okay? Just so you know, these are not equilibrium parts. E is the voltage under non-standard conditions. E naught is under standard conditions. We use 8.314 because we're using joules again. Q is that ratio. When a reaction is at equilibrium, this is important, E is 0, okay? And there's the joke, old chemists never die, they just reach equilibrium. So a dead battery is at equilibrium. Think of concentrations like equilibrium shifting. More reactants means it goes to the products, which means the voltage goes up. Use collision theory and AP question for lies. Okay, so we're just going to plug those in. Now comes the, how good are you at factor label? An amp is a coulomb per second. A Faraday is 96,500 coulombs per mole. And here we go. Calculate the amount of time required to produce 1,000 grams of magnesium metal. So I'm going to start with 1,000 grams of magnesium metal. And I'm looking for time. Electrolysis of molten magnesium chloride using a current of 50 amps. So I want magnesium, and notice here, 1 mg and MgCl2. 24.3 grams of magnesium and 1 mole of magnesium. 1 mole of magnesium, I hope this part makes sense, is 2 moles of electrons. Why? Because really this is kind of sort of magnesium plus 2, right? This is kind of the deal we're looking at here, right? And then what we're going to do here, this is the new one. 1 mole of electrons is 96,500 coulombs. So now I'm in coulombs, but it says calculate the amount of time. Whoa. So now I want to get rid of coulombs. An amp is a coulomb per second. So I want to do coulomb per second, but I'm flipping it around. So if I have 50 amps, I have 50 coulombs per 1 second. And I put it in my calculator. Okay, so again, given mass, the metal you're going to have to deal with its charge. As always, go through moles. Charge of an electron, 1 mole of electrons is 96,500, and you'll never write amps ever, 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 ever. You'll do coulombs per seconds or seconds over coulombs. All right. Chromium plus 3 solution is electrolyzed using a current of 7.6 amps. What mass is plated out after 2 days? So you always start with mass or time, and you're just going to find the other one probably, okay? So if I have 2 days, 2.00 days, I get into annoying conversions. 1 day is 24 hours because I got to get into seconds. 1 hour is 60 minutes. 1 minute is 60 seconds, finally. Now I need something with seconds in it. That something with seconds in it is going to be amps. So I have 7.60 coulombs per 1 second. Okay. So we want to find out what mass of chromium we're at right here, right? So that puts me into coulombs. 96,500 coulombs equals 1 mole of electrons. And then I have to know that there are 3 moles of electrons and 1 mole of chromium plus 3. And then it says what mass, right? What mass? 1 mole of chromium is 52.0 grams of chromium. And I do the math. Needless to say, we do a whole bunch of these problems so that they get more happy with you than normal. We're doing a problem here, and we'll be done. Identify the M and M plus 2 in the diagram and specify the initial concentration of M plus 2 in the solution. I think I'm missing something here. Okay, so looking at this, I'm going to skip this for just a second. Indicate which metal is the cathode and which one's the which of the electron metal is the cathode. Cathode does reduction. Red cat. Reduction is gain of electrons. This is my reduction cathode. It's gaining electrons. Write the balance of electron for that. Somewhere I'm missing my M's and my M plus 2. I feel bad for this now. So I'm going to skip this. But I do know that's the reduction cathode. So this is the cathode. Indicate which metal. So I need to say which metal electrode is the cathode. This is the cathode. What would be the effect on the voltage if the concentration of zinc plus 2 was reduced? Oops, we've got zinc plus 2 and 0.1½ cell containing the zinc electrode. So I'm going to make up this reaction, okay? So let's say that this is the zinc. Didn't we just do a zinc and silver one up here? We just did one. I'll steal that. Was it zinc and silver? Where did it go? No. I did it. I know I did. Zinc and nickel, okay? So we said that, which one did we flip? We said the zinc was oxidized, right? Yes. So zinc is oxidized. So, you know what? We'll just do this when we get the real numbers. 2748 is way too long of a podcast, so we'll finish this off later. Lots of work. Introduction only. Toodles.